Okay, good evening. This is Professor David Reyes. Okay, my topic for this morning, it's this morning already. It will be a long video format discussion on alternating current circuit. We are almost done with alternating current circuit. So the next time around, maybe I will be doing a new topic that is alternating current machines. So we are almost done with alternating current circuit. And the next time around, maybe we'll be doing alternating current machines. Okay, let's proceed. The topic for this morning will be alternating current circuit. This will now be lesson number 36. The title of the topic is still, it's the same as from the past lesson 35. It will be loop equations checked by using Norton's theorem, meaning we are given a problem, we solve it by using loop equations. The last time around, we checked the solution if it was the same as from the loop equations, and we have brought out that they were the same. So for this morning, we will be presenting a Norton solution solving the same problem, okay? And we shall bring out the same solution as from the previous loop equation and Thevenin's solution. Okay, let's go to the final answer before I will discuss the solution. The final answer for this Norton's theorem is actually 16.225. The angle is negative 27.7 degree amperes. That is the solution for this morning. From the previous solutions, the original loop equation problem using loop equations, the answer is 16.225. The angle is negative 27.7 degree amperes. And from the next checking, that is the so-called Thevenin's theorem, what comes out is actually 6.225. The angle is negative 27.7 degree amperes. So we are solving one problem. We had presented 3 solutions so far, and all the solutions are actually same. So hallelujah for the different theorems on alternating current circuit. Okay, let's proceed. The figure of the problem for lesson number 36 will be the same as for lesson number 34 and 35. Okay, so I didn't give you the figure now, but as we solve the problem, I will try to figure out what happens, okay? For step number 1, okay? Under Norton's theorem, we shall disconnect the load, then we short the terminals. So this is a shorting wire, right? Step number 1, disconnect Z sub L and short terminals and compute for I with a subscript is C, meaning total current short circuit. This was actually the given original figure. We have here the load C sub L, right? We remove it for the meantime, then we short the wires. So this is C1, C2, E1, E2 with the polarity indicated, right? So if we short out the terminals, okay, there will be a current that will pass here. If you try to use your ammeter, there should be a current. And the current will be something like this. There will be a current coming from voltage source number 1, and there will be a current coming from voltage source number 2. Because if we try to short out this one, there will be a big short circuit current. That's why the term is short circuit current. There's a big short circuit current. And we could compute for that one by using computations on the board, right? But in actual, you don't have to compute. You just short it, put an ammeter across it or right across it, then try to read the reading. Okay, but we are on the board, we are on paperwork, so we should bring out the solution. The solution should be this current A is going upward, this current B is going upward also, due to source number 1, due to source number 2, So if you try to see it, considering this node here or junction, the total short circuit current, if we short out the terminals, it should be the sum current from source number 2 and current from source number 1. Okay? And since voltage is equal to current times impedance, current now will be equal to voltage over impedance. So we will be using this equation here, right? So the current A will be the voltage of E divided by its internal impedance. It should be a very big value because the internal impedance is a small value. 250 angle 0, 0.6 angle 45, this is 416.67, the angle is negative 45 degrees. Changing this to rectangular, later on we will be having an addition here. So we convert to rectangular already. And for the current B, again, by using the equation I equal to voltage over impedance, the current B due to E2, okay, considering C2, should be E2 over C2. Right? 240 angle 15, 0.8 angle 30. These values here were given from the problem number, lesson number 34 and 35. We are solving the same problem. Okay? So 240 over 0.8, that will be 300 amperes. That's a very big current. Angle negative 15 degrees amperes. Changing to rectangular, this should be the rectangular equivalent. And from the given figure, if we try to consider this junction, the total short circuit current will be the current coming from voltage source number 1, which is A, plus the current coming from voltage source number 2, which is B. Rectangular, we add the real. The overall real will be 584.4. Negative, this is J. So this should be the sum, right? 372.265. Changing to polar. Okay? We know how to change from rectangular to polar. Take the ratio of this divided by this. Trace arc tangent, it will be 32.497 degrees. It should be negative. It's negative. Take the cosine. You divide that value to 584.4. What will come out will be 692.895 degrees. This is a big current. That's why it is a short circuit current. Short circuit current is always dangerous. Right? So under Norton's, step number 1, we short out. Okay, compute for the current. Or in actual, just place an ammeter across it, then read the reading. And what will come out should be 692.895 degrees amperes. Okay. What's next? We short E1 and E2 and solve for C sub n. That's the number 2 step for Norton's theorem. We short out E1 and E2, meaning we short out, right? We short out. So it seems we remove it. Right? So if we remove it, okay, put an ohmmeter at the terminal. Okay? After removing voltage source number 1 and number 2, put an ohmmeter across this. And what you can measure is actually capital letters A with the subscript N, meaning Norton's impedance. And as you can see it, the connection of C1 and C2, they are in parallel. So, in parallel, it should be the product all over the sum if there are only two, right? It emanates from the equation 1 over Cn equal to 1 over C1 plus 1 over C2. And if you try to simplify this one, it should be this, right? But the procedure on how to take the Norton's open circuit impedance and also under Thevenin's, it's the same. So actually, you don't have to compute under Norton's, just copy the value from Thevenin's. And under Thevenin's theorem, the total impedance of C1 and C2 is actually 0.3458 angle 38.59 degree ohms. They are the same. So for both Thevenin's and Norton's, the open circuit impedance are actually the same. Okay? So we got an advantage under Norton's because we will just copy the open circuit impedance under Thevenin's and that's it. Because they are the same. Step number 3. Draw the Norton's equivalent and reconnect ZL and compute for I sub L. Okay? This will be the Norton's equivalent circuit. According to Norton's theorem, the short circuit current source, okay, is in parallel with the Norton's open circuit impedance. Then try to reconnect CL. Okay, we reconnect. Right? So, the connection after reconnecting CL, this Norton's open circuit impedance is in parallel with C sub L. And I think we derived this one from the last time around. The voltage across this should be equal to this, right? The voltage across CN will be I short circuit minus I sub L, okay, times C sub N. That's the voltage across this. It's the current going in times the value C sub N. Using the equation voltage equal to IC, right? And the voltage across C sub L should be equal to I sub L times C sub L. We equate the voltage here to the voltage across the load. And if we try to simplify, I short circuit times C sub N, okay? Is it correct? Minus I sub L times C sub N equal to I sub L times C sub L. Okay? This is I sub L. We put it on the right. So we put the equality sign here and this will now be addition, right? Then we factor out I sub L. It should be C sub N plus C sub L. And the right hand side, the left hand side, we put it on the right now. It should be the short circuit current times C sub N. So I sub L now will be the product I short circuit times C sub N all over the sum C sub N plus C sub L. It is 6. Right? So this is now just a matter of substitution. C sub N plus C sub L is actually the same as CTH plus C sub L. Because the open circuit impedance Cn and CTH are actually the same and CL is equal to CL. So actually what we have got under Thevenin's theorem, I can still use it under Norton's, this one. Right? So I sub L now, by using this equation here, it should be the short circuit current. The short circuit current is this one. The almost 693 amperes. Right? Times the value of C sub N. What's the value of C sub N? C sub N is this one. Same as CTH, Thevenin's. 0.3458 angle 38.59 all over. The sum of C sub N plus C sub L is this one. 14.766 angle 33.8 degrees. Maayos silang kagat. Right? So if we try to perform the operation polar multiplication and division, we could try it. 692.895, that's the magnitude, times 0.3458 equals, that's the product, divided by 14.766. Okay, the magnitude is 16.225. That's the magnitude. And for the angle, you take the sum of this. 32.497 negative. Right? This is plus. Plus 38.59 equals, should be 32.497. Should be minus plus 38.59 equals, what's happening? This is a minus, there should be a difference 6 amperes over here. Okay, 32.497 minus plus 38.59 or 6.093. Then we bring out this one. This should now be negative. Okay, right? Minus 33.8. Okay. The angle is 27.7 degrees. Okay. So this angle here is correct. The magnitude is correct. Same as the magnitude using the loop equations. Same as the angle using the loop equations. Same magnitude as using the Thevenin's theorem. And same angle as using the Thevenin's theorem. So actually we have presented 3 solutions solving one problem. And what comes out are actually same answers for all 3. Okay, hallelujah. This is Professor David J. De Los Reyes. Good morning from Los Angeles. Thank you.